We're going to look at some energy changes that takes place as you have two atoms coming together to form an ionic compound. So what this is showing you here is the energy required to remove an electron from a gaseous sodium atom, and that of course would be the ionization energy, the first ionization energy, which is equal to 496 kilojoules per mole. And then for the chlorine atom, gaseous, the energy it requires to gain an electron would be given by the electron affinity to form the chloride ion, and this is equal to minus 349 kilojoules per mole. Now, based on these two values, one might come to the conclusion that the energy change occurring is so small that it doesn't really have an influence on the energetic favorability of the formation of sodium chloride. However, one important factor that one has to take into account when it comes to determining how stable a compound is the enthalpy of formation of the ionic compound. And that is more important than either the first or ionization energy or the electron affinity for the chlorine. So what we're going to talk about, and you're going to see that in the next slide, is how we can determine the overall enthalpy change using a stepwise procedure, which is known as the Born-Haber cycle, which is basically a hypothetical process showing you how you have the formation of the ionic compound from its constituent atoms. All right? So this is the Born-Haber cycle for sodium chloride. So as you can see, here is designated the start because that's where the original sodium and chlorine is, and the end would be, of course, the formation of the sodium chloride solid. Now, the enthalpy of formation would be, of course, the overall change from the start to the end here, which is equal to minus 411 kilojoules, all right? However, what you're going to see is that the formation of sodium chloride from sodium and chlorine goes through several steps as indicated right throughout this route right here. So what we're going to do is look at each of the different steps and try to describe what is happening in each case. So the first step is where we have the sodium, let me go to my pen here, where we have the sodium solid converted to the sodium gaseous atoms, all right? And the conversion from the solid to the gaseous state, we call that sublimation. So the delta H1 here, which is equal to 107 kilojoules, that is basically the same thing as the enthalpy of sublimation of sodium, all right? Then the next step is where we convert the chlorine molecules to the chlorine gaseous atoms, right? And that would be the bond dissociation energy. Now, in the case of this example here, you'll notice that there's a coefficient of half here, right? So therefore, the enthalpy change here would be half the bonding energy, the bond dissociation energy of chlorine, all right? And that would be equal to 122 kilojoules here, all right? The next step is where the sodium gaseous atoms is converted to sodium gaseous ions. In other words, we're talking about the first ionization energy for sodium, all right? Because of course, in order for this to take place, an electron must be lost, all right? And then now the next step is where the chlorine gaseous atoms here are converted to the chloride gaseous ions. And that of course would be the electron affinity for chlorine gaseous atoms. And then we get to the last step. So the last step is where we have the reaction between the sodium gaseous ions and the chloride gaseous ions to form sodium chloride, which is the final product. Now, the enthalpy change for that reaction here is minus 787 kilojoules, all right? Now, let me here, at this juncture, define what is known as the lattice energy, which is what is occurring here. The lattice energy, let me do this here, delta H lat is known as the lattice energy. And this is a measure of the stability of the ionic compound. and it is the energy that is required for the breaking up of the solid ionic compound into its constituent ions. So this is basically what happens. All right? So the energy required for this is called the lattice energy. Now in this particular case, the lattice energy would be from the sodium chloride to the ions. So it would be the opposite direction, going in that direction, right? So this minus 78, I'm sorry, I keep saying 78. This minus 787 kilojoules would be equal to minus the lattice energy, all right, for sodium chloride. So basically, if we want to find out the relationship between all of these terms, you'd see that this here would be equal to the sum of 107 plus 122 plus 496 plus minus 349 and then plus minus 787. And that sum would be equal to this value right here. And the reason why we know that is because of Hess's law, all right? You'll notice a question being asked here. Let me go back to my pointer. Okay, what's going on here? Right, the question being asked here is what law can be used to find the enthalpy change that occurs in the steps? And the answer would be Hess's law, all right? Hess's law basically says that the enthalpy change going from the start to end is independent of how you get there, be it directly or be it through several steps. And that's basically what we looked at. If you add up the 107 to the 122 and all these numbers here, that would be equal to minus 411. Now, as I said before, the lattice energy is a measure of how stable the compound is. And that's why it says here delta H5, which is going from the sodium and chloride ions to form the product. That would be a very large negative number, all right? And let me just say here, because this might be a source of confusion for some of you, in some textbooks, they express a lattice energy as being the energy that is released when the ions come together to form the solid compounds. However, in your textbook, the textbook that is the OpenStack textbook that is available in Canvas, the definition in that textbook, when you look it up, it's the other direction that they're referring to. It's the energy required to break up the ionic compound into its constituent ions, all right? Okay, so with that said, we're going to stop this video here. And the next video is where we're going to look into this example right here, all right? This is the example we'll be looking at. And this is where you're going to see how we can use the Born-Haber cycle to determine the lattice energy of magnesium fluoride in this example based on the data that is provided. Okay, until next time.